That is first year anatomy. Second year. क्या करायचं होतं? सेकंड इयरचे प्रॅक्टिकल 3 असतात. फिजिक्सचा 3 असतं यायचं.
On descendants in design. Welcome all of you on the second day of this international workshop on descent rates in nuclear science and material science. Welcome all the participants, dignitaries and delegates joined us from the globe. Welcome, Gaikwad sir. So let us start our first session of day 2. I request Dr. A.R. Gade sir to please introduce our resource person, Dr. D.K. Gaikwad sir, who is joined us from the ACS College, Dharangaon, Jalgaon. Please, Gade sir.
Thank you, sir. Good morning, all. I am here to introduce today's resource person, Dr. D.K. Gaikwad, sir. Am I audible, sir?
Yes, sir, you are audible.
Shrikant, sir, am I audible?
Yes, sir, you are audible. Please go ahead.
Thank you. Good morning, all. I am here to introduce Dr. D.K. Kakade, sir, currently working as an assistant professor. Sorry. Dr. D.K. Kakade, sir. Dr. D.K. Gaikwad, sir, currently working as a assistant professor, Department of Physics, Arts, Commerce and Science, Dharangaon. He has completed his PhD from Department of Physics, Dr. Babasaheb Ambedkar, Marathwada University, Aurangabad, entitled Gamma Ray Spectrometer Investigation of composite as a radiation shielding material under the guidance of Dr. Pravina Pawar Madam. He has 40 plus national and international publications from different indices like Science Citation Index, Care List journals with 1500 plus citations. He has attended 30 plus national international conferences and workshops. He has awarded as a Rajiv Gandhi National Fellowship. Thank you, sir, being with us. Now I request to Dr. D.K. Gaikwad, sir, to start his session.
Thank
Dr.
you,
D.K. Gaikwad.
Dade, for nice introduction. Thank you, all of you, for inviting me. Let me share the screen. Is it visible?
Yes, sir.
I welcome all of you on to the international workshop on recent trends in nuclear science and nuclear science and material science. You see, well, we are living in the age of glass. How we are using the glasses, and the glasses has occupied the most of the space in human life. So that's pretty much convincing to we are living in the age of a glass. By the name of the material, we have the invention of material, the discovery of material, we given the name of the age. The earliest in the Stone Age, the human used first glass, that's called Austin glass, for the weapon and jewelry purposes. Or the discovery of different kind of materials, and then given the name of these ages. And see, in the early in 1080, the first time there is a rapid development in the glass. Now, in the 19th century, the steel concrete were invented and in use in the construction of buildings and other things. Then, if you move further in today's age, we are tremendously using social media and other platforms. And here, over the age of over different ages, the popularity of glasses diminishes yet. The other glasses were formed while formation of universe. See, this glass was formed. This glass was formed by lightning. Lightning stuck to the sand, and the sand melted by this lightning, and then this molten sand were immediately cooled by the surrounded water, and then this fulgurite glass formed. This structure is formed, and the structure shows the flow of lightning. And then similarly, this white dendrite structure, you can see this is also a fulgurite glass. This is formed because of the lightning. Lightning melt down the sand, and then immediately pulled by the surrounding water, and you get such type of structure. Similarly, you can see at the bottom of this structure is also the fulgurite glasses. You see the black structure. This is the first time human used this glass, Austin glass, for the purpose of the jewelry. Then for the weapon purposes, the human first time used in early age. The human used this Austin glass. You see, over a period of time, the glass were developed and it has been developing until the date is the scientist is inventing a new kind of glasses. The first time around 500 BC, first glass called Austin or Tektite glasses were used by human as jewelry, weapons, and other purposes were found in Syria. Then, as we move further, in around 220 BC, the first glass were synthesized by blowing blowing glass in a mold, and this was found in the Syria. Then, in 180 in Rome and France, in Germany, the first glass, clear glass, were synthesized for Windows application. Then first time in history, around 1650 AD, the oxides were incorporated into the glass system, and there the first lead oxide were incorporated into the glass in England for the high quality glass. Again, here in the development in 650 AD in England, the various kind of oxides were tried to incorporated into glass for to produce a high quality glass and desired application glasses. Then, as we move further, and in 980, the first rapid development and first scientific tailoring of glass were done in Germany, and therefore the scientific industrial society were attracted great attention because of its well-determined composition according to the need of the glass. Then the 1980, the first time the flat glass were directly synthesized by molten liquid by rolling method in Belgium, France. Then you see the glasses can classified into different types. First is the organic glass, and then inorganic glass, and then metallic glass. Organic glasses can also be called the thermoplastic. One of the examples is PMP is the one of the organic glass. Then metallic glasses is also very important, and the metallic glasses has the high conductivity. Then third type of glass is a inorganic glass. You can see the inorganic glasses again further classified into three categories called, one is the oxide glass, hybrid glass, and non-oxide glass. The oxide glass is one of our interest area. So here in oxide glass, we have the wide variety of oxides are available for engineering the different kind of glasses. In oxide, basically the silicon oxide, borate oxide, phosphate, and another heavy metal oxide like bismuth oxide, lead oxide are also the choices are available in the oxide depending on the application of the glass. We can place the oxides. Then again, hybrid glasses. Hybrid glasses can be synthesized using the oxynitride, oxyhydride, and oxycarbide. Then third one is the non-oxide glasses. They can be halide, chalcedonide, and nitride glasses. So our interest is a oxide glasses over here. So depending on the composition of glasses, it has a wide different applications. See the bottle glasses, and then the laboratory glasses. The laboratory glasses are say Pyrex glasses, or sometimes we use borate glasses for chemical thermal resistance. Resistance property of this particular glasses are very good, so we use the borate glasses and Pyrex glasses for the laboratory purposes. Again, we can draw a wire from the glass material. So you see, this is the optical fiber. which is one of the application of a glass material, and we can see the internet is spanned over the world because we see the signals can be transmitted very speedily using the optical fiber. Again, depending on the chemical composition, we can synthesize the Windows classes. You see this, you may be familiar with this picture, and this picture is of a Burj Khalifa. You see the panels, glass panels on this building is are designed for thermal resistance purpose. For thermal resistance purpose, you can see we can use the aluminum oxide for thermal resistance, or depending on the other purposes of a say Windows glasses, we can synthesize. Then another application of a glass is a bioglass. First time, because of the efforts of scientist Hench in 1960, he conducted number of investigation with the army funding, and then he conducted and he concluded that the glasses can be used in a and he studied the bioactivity of a glasses. And after that, the rapid development of bioglasses were done, and then the glasses can be used in a drug delivery, antimicrobial, and orthopedic, dental, and cardiovascular applications. Then immobilization of nuclear waste in a glass matrix is one of the important application of a glass. You see, the vitrification of nuclear waste it can be reduce the volume of a waste, so it is very sophisticated way to store a nuclear waste, and therefore, if the nuclear material is immobilized into the glass matrix, so then it cannot be easily escape the glass matrix, and we can avoid the contamination of radioactivity. And so you can see the glass has the high durability, and it can long last more than, as we see, the glass can be long last billions of years. And see, you see here is the black glass. This is the glass is vitrified nuclear waste glass, and see it is very easy to store we can say the nuclear waste management can be efficiently can be done using the vitrification technology. The radiation shielding glasses is one of our interests. There is a wide variety of radiation shielding glasses are available. Still, scientists are inventing the new kind of radiation shielding glasses depending on the radiations. See, the radiation shielding glasses, as we have been working in this radiation shielding glasses. So depending on the radiation applications, there is a wide variety of oxides are available. Say from heavy metal oxide to low jet oxide materials. But what we have to do here for synthesis of radiation shielding glasses, just mix the definite or determined quantity of oxide and make a batch of this oxide, particular specific batch of oxide, and then we transfer this batch to alumina crucible, and this alumina crucible then transfer to a furnace for oxidation purpose. So oxidize this this mixture for 1 hour, or depending on the composition of a glass. Then the oxidized mixture then placed into the in a furnace for high temperature, then melt the mixture, and then shake this mixture frequently to avoid any bubbles or any say the inhomogeneity into the melt. Then the molten liquid then transfer to the quench, and then to mold, and then the mold we can get in the mold we can get the a glass. Then again, this glass is transferred to the furnace for annealing at different temperature depending on the composition for 5 hours for to reduce any traces into the glass. So how this is the how we can get the glass. Then as we synthesis the glass, and then we have to find out the radiation shedding capacity of the glass, then we can perform the nuclear transmission experiment. This is the transmission experiment. Here in this experiment, we use the sodium iodide helium detector here, detector, and these are the collimator. These are the collimator, and here we can put the source, our radioactive source we can put over here, and this is the very narrow orifice of this collimator, and then we place collimator in front of this orifice, and then these are, you can see these are the different collimator and with the different orifice. Then here we put our sample, and then we irradiate our sample directly to the gamma rays, and then gamma rays interact with the sample, and then here we can detect the count. To measure the radiation shedding property, we measure intensity of this source by with this sample and without the sample, and then we can measure we can get a count over we can measure the count via the detector, and then we can get such type of spectra by placing the this barium, cesium, and cobalt in a source folder. Then we can get this type of a spectra. We got this spectra right now, and we measure the intensity of with and without the sample. We call initial intensity. This is for without the glass, and then I is a with the glass. By putting this formula, we can find out the different properties of a material, let's say radiation shedding properties of material. And then we can verify our study using a theoretical tools are available over there. And another tools are available. Even we can try a MCNP code, as a previous speaker has already been discussed with us. See, this is one of the study. What we have done, we collected the spectra with and without glass. This is for 0.356 mega electron volt, and these are for the 362 mega electron volt. These are for the different energies we have got this. We have seen that this black bubble shows the without the sample, and this red bubble shows the with sample. So with sample we get very low count. This means that there is a attenuation of a radiation by the glass. Again, this is our study, and we have compared our study with the another standard glasses, and we have found, you see, different energies. These are our red balls are our samples. You see all the here. You see, we have determined the mean free path of a glasses. Our glasses are the bored glasses particularly, and our bored glasses were compared with the zinc and lead glasses. Most of we compared our glasses with the lead glasses, as lead has a very high attenuation capacity. You see, the mean free path of all glasses, that is we compare our glasses with the all glasses, that is lead glasses, and here our sample has a low mean free path in 356. Here our mean free path of our glasses is exactly equal to the lead silicate aluminum glasses. At low energy, At low energy, our glasses has the comparable capacity with these other glasses. As we increase the energy, if we move towards the 6 kilo electron volt, you see the glasses has low mean free path. Here again, you see these glasses has a mean free path at chemical composition 25 and 20 mole of 20 and 25 mole percent of a bismuth, we get the very low mean free path. Again, if you see at bismuth composition 10 to 15 mole percent, then the mean free path is a very much, or say we can say a comparable to the other aluminum lead silicate glasses or another heavy metal glasses. Again, if we increase the energy, we can see the mean free path of all synthesized glasses. You see, as all synthesized glasses is very low. Again, here at very high energy, you can see the mean free path is a very low than the another glasses. Mean free path is low means there is the high shading capacity, right? So we seen that the all lead and heavy metal oxide glasses has the high mean free path than the synthesized glasses, and then we can say that the synthesized system has the good capacity to reducing shading capacity than the other lead and other zinc glasses. Then another study, we synthesized tellurium based glasses and compare our glasses with S1, S2 is a glass, blue glass, and 456 is a concrete. These 456 are the still concrete, and these are the ordinary and heavyweight concrete. And this Z1, Z2, Z3, and Z5, Z4 are tellurium glasses. If you see the Z1 here in this case, in the very first diagram shows the reducing shading capacity or the half value layer is incomparable with the other glasses, but the half value layer of the synthesis glasses is very low than the concretes. Let's see in all diagram you can see all figures, you can see the HVL of a glasses is higher, is lower than the concrete, but you see the HVL of this synthesized glasses are comparable with the other glasses S1 and S2. So we can say that the synthesized glasses has good shading capability than the other concretes, and but comparable with the shading glasses. Then again, we compare another glasses, tellurium, Augustin tellurium lead glasses with other glasses in wide energy range. We can say that initially with the energy that HVL slowly as you see up to 10 raised to the power -1 mega electron volt, the HVL remains independent of energy. As you further increase the energy, then it slowly increases with the increase in the energy. We get the highest HVL here at this. Hello. So
Yes, sir.
here then we get the highest HVL at the 10 raised to power 0, or we say approximately at approximately at 1 mega electron volt. Again, if we move further, we increase the energy, then the HPL decreases with increase in the energy. We can observe with all samples. Okay, so we compare our study with the lead classes. You can observe in the all figures, and here we can say that the HBL of our sample is in low energy range is comparable with the other classes, but high energy, which is very high, right? So here we can say that the radiation shielding capability of our glasses is comparable, and we have been found that the radiation shielding capacity of a newly developed shielding glasses. Thank you, doctor. Thank you for having me. Thank you for inviting. Thank you for your invitation. I'm really thankful for the Arts, Commerce, and Science College Kiledharu for inviting me for this. Yes, thank you.
Thank you. Thank you so much, Dr. D.K. Kakar, sir, for such a nice presentation. Thank you so much, sir. Now I request Dr. D.S. Zare, sir, to please introduce our next resource person, Honorable Professor Dr. Pravina Pawar, ma'am.
Sir, I have a query.
Dr. D.S. Zare, sir. Yes.
Dr. Ram, sir, please wait. Audience having a question. Yes,
Yeah.
sir, please.
Yeah. Hello,
Please.
sir.
Hello.
Zare, sir, wait.
Hello,
wait.
sir.
Zare, sir, wait. Audience having a query.
Sir, I have a query regarding the shielding property. Is there Gaikwad, sir, is available there, sir?
Yes,
Yes, sir, yes, sir.
Yeah, and good morning, sir. I'm Dr. Ashwajit from Davangere University, Karnataka. So, whatever the presentation you have made is a very good presentation, sir. But regarding the shielding property, what is the size is required of our glass sample to do the characterization of gamma ray shielding?
Or sample, you're asking about sample size, right?
Yeah.
See, we use from 0.2 mm to 1.5 mm. We can try this range.
Because the characterization you have made, the analysis part, the mean free path, it is in the range of something 4 centimeter, the mean free path you are expressing. So that's what I'm looking for, the size of the sample.
Yeah, right. You're right. This was a theoretical study. You seen 4 mean free path was a theoretical study, right?
Okay. Sir, and another one question, sir. The glass processing system you have explained through the flow chart. So in that you are mentioning that the preheated steel plate we are going to power the molten glasses.
Right,
so
sir.
why it is required the preheated plate only, sir? Why not in the room temperature we have to power? So,
Okay, there may be glass may be cracked directly, so we avoid to
means for the preheated things we need not worry about the annealing.
no, not worried about, not like that. But if we keep a preheated say mold, then we can easily remove the stresses. Annealing is there required again, but we can synthesize our glass stress freely.
Sir, even I am also working on that oxide glasses only, sir.
Yes,
So
sir.
that's what the lot of the researchers has been made on the preheated plates only. I have the query: what is the role of the annealing? So that is also the removal of thermal strains only, no?
So we cannot remove all stresses directly. If the glass is cool over a time, then again there is a stresses, right?
Okay.
So it needs a very long time to remove the stress. So we have to cool the glass,
Okay.
right?
Okay, sir. And the software you have used WinXCom for the gamma ray shielding, is it available for free or
Yes, sir, this is open source software.
oh, okay, sir. Okay, sir. Thank you, sir. Thank you.
Is there any other question? Audience, please.
Yes, sir, no.
Please ask your question. think there is no any other session, no any other question. So I would like to thank you, Dr. D.K. Gaikwad sir, for this wonderful session. Session was very informative and for this young researcher. So I'd like to thank you once again. Thank you, Dr. D.K. sir.
Thank you, sir.
Ma'am is joining us soon. May I request participant please go through your YouTube link. Please, participants are more here, so that's why the resource persons are not able to join. I request participants to please join our YouTube link. Yes, ma'am has joined us. Okay. Welcome, ma'am.
Government.
Now I request Dr. D.S. Zares sir to please introduce our next resource person, Honorable Professor Dr. Pravina Paur ma'am, who is a professor from Department of Physics, Dr. Babasaheb Ambedkar Maharashtra University. Please, Dr. Zares sir.
Yes, okay. Good morning, everyone. I'm audible.
Yes, sir, you are audible. Go ahead.
Yes, yes.
Yes, thank you. Good morning, everyone. I am Dr. Dilip Zare, Head Department of Chemistry, Bhagwan Mahavidyalaya, Asti. It's my pleasure to introduce Dr. P.P. Pawar, Madam, Professor in Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, for today's second session of this international work on the recent trends in nuclear physics and material science. Madam has 13-year teaching experience in physics department, Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. She has currently working on nanomaterial as a nuclear medicine used for cancer treatment, radiation therapy, gamma ray interaction studies of nanomaterial, cobalt ferrite nanoparticle pellet synthesized using the cost-effective sol gel auto-irradiation at 2 irradiation on structure, morphology, and mesoporosity. Power Madam has vast experience of research in nuclear physics. She published 79 research papers in national and international journal, conference, seminar, workshop, etc. She is also life member of Indian Physics Association, life member of Journal of Astronomical Society of India, New Delhi. Life member of Indian Society for the Radiation Physics, June 216. Madam also participated in extracurricular activities. She is awarded by first grade paper presentations in international conference on recent development in engineering science, management, and humanities at MB College, Latur in India. She is also awarded by the Lokmat Sakhi Gaurav Puraskar 215 for excellent work performed in educational field. Research project ongoing completed in infrastructure created near about 22 lakh sanctioned amounts. Under the guidance of Madam, 7 students working for PhD and 8 students awarded PhD. The patent and consultancy work is in progress with medical college, hospitals, and agriculture institutes. So I heartily invite Dr. P.P. Madam, Pawar Madam, to deliver her knowledgeable lecture having title is gamma rays interaction studies with matter. Power madam, please to continue.
Who this is?
Hello.
Hello.
हे फक्त स्क्रीन चालू आहे.
व्हिडिओ पण दिसतोय साईडने.
आता ते दुसरं नाही.
Please start your camera.
सर व्हिडिओ कुठून नव्हतं?
ते त्याच्यात स्क्रीन आणि याच्यात व्हिडिओ.
दिसतोय? Yes, you are visible, ma'am.
व्हिडिओ नाही दिसतोय. ओके. गुड मॉर्निंग. हॅलो.
Yes, you are audible, ma'am. Go ahead.
Okay. Hello, myself, Dr. Praveena Pawar, professor in the Department of Physics. Today, I am going to deliver a lecture on the gamma ray interaction with matter. First, I congratulate Ram Bhosle, my student, for arranging such a nice activity, and also congratulate to co-organizer DT Wag sir, DK Kakde sir, Dhonde sir, Zare sir, and Dhine sir for arranging such a nice activity.
Thank you, ma'am. Hello, ma'am.
Huh.
Yes.
So today's topic is gamma ray interaction with matter. In this topic, outline of my presentation is, first we will discuss about the radiation, then life and radiation, nature and origin of radiation, types of radiation, radiation units, standards, then ionizing radiation, health effect, categories of exposure, reducing exposure, then radiation protection, interaction of gamma rays with matter, and finally discuss about the softwares for shielding effectiveness. Okay, so come step by step. First, we will see what is radiation. Here, radiation is the energy that travels in the form of waves or particles and is part of our everyday environment. Radiation is everywhere. It is in the air we breathe and the food we eat. See this figure showing the radiation. Here, radiation atoms, energy, radiation, and particles. Life and radiation. All life is dependent on small dosage of electromagnetic radiation. For example, photosynthesis and vision use the sun's radiation. Then people are exposed to radiation from cosmic rays as well as to radioactive materials found in the soil, water, food, air, and also in inside the body. Radiation sources are widely either useful or harmful depending on its use and control. See this figure showing this atom, an electron, proton, and quarks nucleus. Now
Your voice is not clear, ma'am. Hello.
Your voice is not audible. Maybe something there is any technical issue. It will be resolved within a fraction. Please wait.
There is some problem. Wait for a minute. Technical issue is there.
नेटवर्क का प्रॉब्लम चल रहा है.
ठीक आहे, याच्यात ना घेते
स्क्रीन
स्क्रीन त्याच्यात ना दाखव. ओके, am I audible? Hello,
Yes, ma'am.
Ram?
Yes.
Yes, ma'am, you are audible.
Yes, ma'am, you are audible.
Okay, the nature and origin of radiation. Here, there are
Ma'am,
various
please,
kinds of.
Share your screen.
Yes. Please share your screen. Your screen is not visible to the participants.
Okay, my student will share that screen. Till now, I will
Okay.
continue. Okay.
Okay, ma'am. Okay, no problem.
See the nature and origin of radiation. There are various kinds of radiation which can be classified in electromagnetic radiation and particle radiation. Okay, so here ionizing radiation, visible non-ionizing radiation, cosmic rays, gamma rays, X-ray, ultraviolet, infrared, near radar, FM, TV, short waves, then broadcast, power transmission. In wavelength in meters, so high energy electron volts to low energy electron volts. Now the types of radiation. There are two here: non-ionizing radiations and ionizing radiations. The ultraviolet, visible, infrared, microwave, radio, and TV power transmission. And ionizing radiations, the radiation capable for producing ions when interacting with matter, X-ray, alpha, beta, gamma, and cosmic rays. In case of non-ionizing radiation, the sources are ultraviolet light, visible light, infrared radiation, microwaves, radio, and TV, and power transmission. Okay. So in non-ionizing radiation, the examples are ultraviolet, black light, induced fluorescence in some materials, vision, very small portion that animals use to process visual information, heat, infrared, a little beyond the red spectrum, then radio waves beyond infrared, microwaves, electrical power transmission, 16 cycles per second with a wavelength of 1 to 2 million meters. in ultraviolet sources, sunlight most
Excuse
harmful.
me, ma'am.
Okay.
Ma'am,
Yes.
sorry to interrupt, but your PPT is not visible, ma'am.
Okay.
Sir, the student is sharing it. He's working on it.
Dr. Ram sir, please make him co-host. The student of ma'am, please ask him the name of it and make him a co-host so that he can able to share the PPT.
Thank you very much, sir.
Yes, yes. Now you can share your screen. Hello.
Yes, ma'am, you can share now screen. Please start.
Hello, sir.
Yes, ma'am. Please continue. You are audible.
Okay, I will continue.
But your screen is still not visible.
Yes, my student is trying.
Yes, sir, you are now co-host. You can share now screen. Yes, ma'am, your screen is now visible. Okay, thank you. Go ahead.
Okay, ma'am.
Unmute yourself.
Okay, ma'am. You can start now.